Welcome back, physics fans. Today we're going to talk about the Biot-Savart Law. We're going to perform three-dimensional integration in cylindrical coordinates in order to illustrate a particular application of the Biot-Savart Law. While three-dimensional integration in cylindrical coordinates isn't necessarily a requirement to meet the course objectives, it may make understanding this application of the Biot-Savart Law a little bit more understandable. In 1820, Danish physicist Hans Ørsted discovered that moving charge, or current, generates a magnetic field. Later that year, French physicists Jean-Baptiste Biot and Félix Savart created a mathematical model that expresses this magnetic field. Here is the Biot-Savart Law. The variables involved are the permeability of free space, the current in our wire, some infinitesimal length vector within our wire, a unit vector, r hat, and r squared, with r being the separation distance between the point in space that we're trying to express the magnetic field and the current carrying wire. Before moving forward, we should note a few things about the Biot-Savart Law. First is that it will require us to perform path integration along the length of our current carrying wire. Additionally, we will have to cross our infinitesimal length vector with some unit vector r. This unit vector, of course, has a magnitude of 1 and has a direction that is oriented from our current carrying wire to the point in space we wish to express the magnetic field. Finally, the magnetic field is inversely proportionate to r squared, where r is the separation distance between the wire and the point in space. What this means is that the magnetic field will decrease exponentially the further we get away from the wire. In its most basic form, the Biot-Savart Law can be difficult to work with depending on how complex the geometry of our wire is. In PH255 and PH255, we'll apply the Biot-Savart Law to several particular geometries. Let's focus on one of those geometries now, known as a solenoid. A solenoid is a coil of wire with some constant inner radius oriented on a fixed axis through its length. One way to think of a solenoid is as a rigid slinky. Because the turns, or the loops, within a solenoid are tightly wound, we can approximate a solenoid as a stack of wire loops. Let's calculate the magnetic field generated at the center of a solenoid, point P. The solenoid has some inner radius r and some total length L. Additionally, the solenoid has a current that is flowing in the direction indicated by the arrows through the loops. Due to the geometry of our wire, it will be easiest to perform this integration using cylindrical coordinates, where S represents the radial direction, phi represents the azimuthal direction, and Z represents the direction aligned with the longitudinal axis of our solenoid. Before we can apply the Biot-Savart Law, we'll need to define the terms of our path integration. Let's consider an alternate two-dimensional view of our solenoid. You can see here that the blue circles represent the edge of our solenoid, with the direction of the current flow indicated by the notation. Additionally, we have point P labeled at the center of our solenoid, which is located some distance capital R, the inner radius of the solenoid, from the edge of the solenoid itself. Point P is located some distance lowercase r from an arbitrary point on the solenoid, and our inner radius of our solenoid and our separation distance from the edge of the solenoid to point P is separated in the vertical direction by some distance z. Our coordinate axes are labeled for this diagram with the right direction indicating our radial direction in cylindrical coordinates and the upward direction indicating our longitudinal direction for the axis running through the solenoid. We can see from our two-dimensional diagram that we can express the separation vector lowercase r using the inner radius of the solenoid, capital R, and the vertical displacement z. We can express the magnitude of that separation vector using the Pythagorean theorem to achieve this expression here. To find unit vector r, we simply take vector r and divide it by its magnitude to achieve this expression. Our next step is to express the magnitude of our infinitesimal length vector, dl. Again, dl is some infinitesimal length as we integrate around the path formed by each of these wire loops. Because we'll be integrating at some fixed radial distance, capital R, we can express the magnitude of our infinitesimal length vector, dl, using this expression right here. The factor capital N divided by capital L comes from the fact that each infinitesimal length is going to have some number of turns from the solenoid associated with it. Now we're ready to take the cross product of our infinitesimal length vector dl and unit vector r hat. We can establish the direction of dl by understanding the direction of flow of current flowing through each of the wire loops. The result of that cross product can be seen here. Now we have everything that we need to apply the Biot-Savart law to our solenoid. If we take our expression for the magnitude of lowercase r and the cross product dl cross r hat and substitute them into the Biot-Savart law, we arrive at this expression. I'll leave the integration as an exercise to you, the viewer, but I will note that a table of indefinite integrals would come in extremely useful in simplifying this expression. The result of that simplification can be seen here. The final step of this application is to assume that the longitudinal length of our solenoid, capital L, is much greater than the inner radius, capital R, of our solenoid. If we do that, the term r squared in the denominator drops out because the magnitude of capital L is much greater than the magnitude of capital R. If we simplify this expression, we arrive at the expression for the magnetic field inside of a solenoid, which is the same expression that you have on your physics reference card. I would like to point out that inside of a solenoid, the magnetic field only has a component in the z direction. All components in the radial direction canceled when we performed our integration. As one final comment, I'd like to point out that we will not expect you to perform this integration on any major graded events in PH205 or PH255. This is simply meant to express where the equation on your physics reference card was derived from. Let's put our derived expression for the magnetic field inside of a long solenoid to test over in the lab. For this experimental setup, I've acquired a solenoid of approximately 150 millimeters in length. The solenoid has 477 turns, and you can see that I've electrically connected the solenoid to the lab bench. Initially, I'll provide 5 amps of electrical current to the solenoid, and I'll use the magnetic field sensor to measure the magnetic field within the solenoid. So the first step is to turn on the current. I can verify that there is a magnetic field within the solenoid by taking a small permanent magnet and bringing it close to the opening of the solenoid. You can see that the magnet was sucked inside the solenoid because the permanent magnet is trying to align itself with the magnetic field within the solenoid. Now let's go ahead and start our Pasco experiment. And we'll place our magnetic field sensor within the solenoid. You can see within our Pasco experiment the magnetic field has leveled out and is measuring within the solenoid approximately 0.018 Tesla. So that's the magnetic field with 5 amps of current. So now let's go ahead and increase the amount of current flowing through the solenoid to 10 amps. And once again, I'll run my Pasco experiment. And we can now see that the magnetic field within the solenoid has increased
to approximately 0.035 Tesla. If we apply our equation derived from the Biot-Savart Law, we find that the magnetic field is approximately that which we've experimentally measured. If you have any further questions, please direct them to your instructor. As always, may drag be negligible and the net force be with you.